Hello, in this short video, I'm going to show you a seemingly simple program that should work just by looking at it. But when you run it on the hardware, you realize that there is a surprise. And so it's a rather simple setup. I have gone ahead to write the code. And by the way, this project is created for the STM32 F407G Discovery 1 board. However, it doesn't matter what microcontroller unit you are using as far as it's an STM32 MCU or dev board. You just have to choose the right target when creating the project and everything is going to work fine. So you should be able to replicate what I'm doing here without any struggles. You look at this program and you can agree with me that even somebody who started programming just yesterday should be able to understand this program here. It's simple, right? So on line 8, I'm declaring a floating point variable called A. And on line 9, I'm doing the same and storing a different value in a variable called B, which is also a floating point number. And on line 10, I have a floating point variable called S, basically sum, into which I want to store the sum of A and B, right? This program should work. However, when we run it, there is a surprise. So I'm going to debug this program. We see the surprise. I explain the surprise, and then I'll also show you how to fix it, okay? So I'm going to click on this debug button here. And you can see that the program has compiled successfully because as far as the compiler is concerned, this is a valid C code. The problem comes up when we want to run this on the processor. So on your right here in the variables expressions window, you can see the content of each variable. The breakpoint is currently on line 8. What that means is that line 8 hasn't executed yet. And so the value here isn't really what I've stored in there. At this point, you can step into or step over. For these simple instructions, it doesn't really matter whether you step into or you step over. So I'm going to do step over. Now, looking here, you can see that A has been declared and the value 34.5 has been stored in it. All good to this point, right? Now I click on step over again to execute line 9, and you can see that 90.8 has also been stored in a variable called B. Now, line 10 is where the surprise lies. For line 8 and line 9, we were just declaring and storing something in memory. And so it doesn't really place any burden on the microcontroller to perform floating point calculations. So it works perfectly fine. Now on line 10, we are trying to add what's in A to what's in B and store the result in S. I'm going to execute that. And boom, this is where the surprise comes up. If you look at the assembly code, it has gone into an interrupt handler or an exception handler that is known as the default handler. And what is happening here is that the program is in what many programmers will call a crash loop. Basically, it's in an infinite loop. You can see on line 116 that there's a label here called infinite loop, and the instruction on line 117 is basically saying A should branch to the label 116. So basically it keeps calling itself over and over and over, and at this point your processor has no ability to do anything else because it is caught up in this loop. Now the question is, why would such a program not run? Why were we able to store floating point values in variables A and B, but the challenge only came up when we attempted to perform actual floating point calculations in our program? This is where knowing about your microcontroller unit becomes very important, right? So the secret here is on STM microcontrollers, there is that dedicated unit that handles floating point calculations. and it is not enabled by default. What it means is that when your board is reset, okay, or when your MCU is reset, you power it on, and it begins to fetch your programs and executes them. It doesn't automatically enable the floating point unit. And so this is where you have to find out how to enable the floating point unit before you are able to perform floating point calculations. The question is, how do you find out this information? If you remember, I said the FPU is a core part of ARM processor. So what it means is that this is devoid of the manufacturer. It doesn't even matter whether it is ST Microelectronics or it is Texas Instrument or any other manufacturer. Again, remember that ARM is the company that designs the architecture, and they sell the licenses to actual manufacturers to manufacture boards and MCUs out of those licenses. So when we say something is a core part of ARM, it means it is not coming from the manufacturer. So whether you buy an ARM-based processor, and by the way, my processor or my MCU is a Cortex-M. So regardless of whether it's from Texas Instrument or from ST Microelectronics, it is going to have the FPU in there as far as it is stated as part of the specifications for that particular MCU. So now we need to figure out, how do we enable this, okay? So the way to fix this problem is to look into the documentations that comes with your board or your microcontroller unit. Now, one thing I like about the STM32 Cube IDE is how the documentations for your particular target MCU or board are bundled once you select your target during the project creation phase, okay? So that, I mean, it saves you from having to go online, figure out how to find what, right? So I'm going to show you how to do just that. You go to help and configuration tools, I think, yes. Bad place to put this, but that's where it is. And you go to target device, docs, and resources. So this opens this window, and you can see there's the MCU pad and there's also the board. The board has documentations that are specific to your particular dev board, if you are using a dev board, by the way. But if you aren't and you made your own hardware, you can also go to the MCU and you're going to see all sort of documentations there. What we are looking for is called the programming manual. In this particular case for my board, it is labeled PM0214. Yours would be different, but you will still find it here, right? So you click on this and it downloads it for you. And as you can see, I have already visited this page, so it came there directly. But if you're using the same board as mine, then you go to page 252. Otherwise, just search for FPU or floating point unit on your computer or in the PDF, and you should land on the page that is necessary. Now let's do some short reading here. It says the Cortex-M4F FPU implements the FPV4SP floating point extension. Basically, what they mean is that this particular unit in your MCU has what is known as extension registers that helps the entire microcontroller unit to perform floating point calculations. And this FPU is not on by default, as I said. When your board is reset, right, and it starts executing your program, the FPU is not enabled by default. And so you have to check which registers should be set, which register is your target, and also which bits in those registers should be set and how they should be set to be able to enable floating point units so that you can perform floating point calculations. Over here it says coprocessor access control register CPACR. This is where you need to go. And if you read this, it says it requires privileged access, and then the CPACR register specifies the access privilege for coprocessors. Basically, it tells you that you need to set CP10, CP11 to 111 for full access if you want full access. So I'm going to set all the bits from bit 20 to 23. So that is 4 bits, right? So 20, 21, 22, 23. 4 bits starting from bit 20. I'm going to set all of them to 1, and this is going to basically enable the FPU so that our program is going to work. Before I write the code, I'm going to do something small in Rust to show you what I'm going to do in C. So you don't need to understand Rust here, but the output is beautiful, so I just want you to see. So what I'm going to do is I'm just going to do this. What I'm doing here is 0xf. Okay, this one is 15 in hexadecimal, and 15 in binary is 1111. Remember, if I have a binary number made up of 4 bits and I set all of them to 1, you sum them, you get 15. So 1111. And then I'm left shifting it to 20. Okay, and I'm going to print it out as a 32-bit binary number. Is this the correct thing? Hopefully. Okay, maybe I should do this here if I remember right. Yeah, beautiful. So you can see that just left shifting 15, 20 positions to the left is going to set the bit 20, 21, 22, and 23 just as is required of us to do. So I'm just going to write this code in C, and that's how we are going to enable our floating point unit. Okay, so I have a header file I've already created here for enabling FPU, and I have a function signature in there. It's called void enable FPU. Basically, you don't give it any parameters. I'm going to enable the FPU, and the corresponding C file is here. And in it, because the CPACR register is in the system control block, you go through this struct that comes from the Simpsons core, and then you say CPACR, and then I am setting whatever is there already. I don't want to clear it, but I'm just setting 1111 to starting from the 20th bit location. So this is automatically going to set 1111 from bit 20 all the way to bit 23, and that is going to enable the floating point unit for me. So having explained this, I'm basically coming here to uncomment this program, and then we debug again. And now you will see that the program is going to run without any surprises. So we are in debug mode once more, and you look at the right side, you see the variables. I'm going to step over. So A has been no, not yet. It was enabling FPU first, yeah, and then A has been declared, B, and then now you can see that we have been able to perform this calculation, and we haven't entered into the infinite loop. Okay, I'm going to restart this debug mode and show you one more thing. So I'm going to go to the registers. I'm going to go to the special function registers, and I'm looking for the registers that comes with the ARM processor that is not specific to STM. And as I mentioned, the FPU is part of these units that comes from ARM. Okay, so if I come here, this is the system control block. I'm looking for CPACR. This is the register we are manipulating to enable floating point calculations. And prior to running enable FPU function, you can see that our target bits are not set in the way that they need to be set. So I'm going to step over to enable that, and I'm going to the next. I think I've selected the wrong register. Yeah, so here, let me restart this so that it makes a lot more sense. Okay, so I have selected my CPACR register, and you can see that our target bit for FPU enabling is not here. We've not activated our FPU yet. Now, if I step over the enable FPU function, you can see that the code we wrote indeed is working. It has left shifted 1111 20 positions to the left, so that fills in position 20, 21, 22, and 23. And doing this gives the coprocessor the highest privilege to be able to use the floating point unit. And then now everything else here remains the same, so I can do my calculations and everything is working. So thank you very much for watching this, and I will see you in the next video.